We're back, and we need to talk about a different type of relationship here. So all this time, all of this talk, we have then talked about the dirty SN2 reaction, that really bad carbon that decided to go out and cheat on its partner. And because it cheated, it saw two things at one time, and it made up its mind on which one to dump, and it always went with the ugliest. That's right, like I said before, it doesn't matter what's on the inside with these compounds. It's all about the outside, it's all about the appearance. And I showed you the prettiness chart in order to determine what would get replaced and what would stay behind on the carbon. Well, I told you in the very beginning there's two different types of substitution reactions. Here we have a cheater, which is what none of us want in real life, right? But molecules are okay with that sometimes. And then we also have a carbon that is not a cheater. Okay, so now we get to talk about a little bit happier relationship here. This carbon's got a little bit of morals, okay? It's got a little bit of conscience. It's going to end the relationship first before it brings anything into the picture and replaces it. What does that mean? Well, let me show you. Let's say that we have a CH3, carbon, CH3, CH3, and maybe a bromine that is here. Let's talk about this molecule for a minute before we go further. Here we still see an alkyl halide, right? I mean, that's what all of this is about. We said it's substitutions of alkyl halides. So we still see the halide. It's right there. And it's still a bromine. And folks, bromine is very ugly. Okay, and the molecule knows that. So this carbon and this bromine that's in that relationship, carbon knows that bromine's not the most attractive thing out there. But, you know, carbon's going to have a little bit of conscience. It's going to have a little bit of moral. It has a little bit of ethic. And it's going to go in and say, bromine, we need to talk. And I think that this relationship is not working. Not for me, not for you. You're very electronegative, bromine. And you want and want and want and want. And you want these electrons. And I just can't give you what you need. So, bromine, I think it's time for us to end our ways. It's time for us to part. It's time for you to go on about your life and let me go on about my life. And this will work out for the best for both of us. And bromine says, okay, not a problem. If that's what you want, whatever. So what we end up with in this type of mechanism is that this carbon, and I'm going to redraw the starting reagents like I always do, all right? So what happens in this mechanism for the SN1 type of reaction? Bromine says, well, before I go, I'm going to stop by the bank and I'm going to take everything that you own. And carbon, it just accepts it. And it goes, okay, if that's what you want to do, go do it. Just leave me alone. And that's exactly what bromine does. So it takes the electrons from the bond, and bromine, whee, goes off and it's now free. Well, in this scenario, carbon ended a relationship, and that was the very first thing that it did. So this bromine goes away, and bromine is not there anymore. Well, the electrons are not there anymore either. And what it leaves behind is a fully charged carbon. It's now a carbocation. So SN1s are going to form carbocations, full carbocations in their mechanism. And that is how they're different than SN2, the cheaters. The cheaters, they don't have enough time to do that. The cheaters see two things at one time, and it breaks up with one while it sees the other one at the same time. It can't form a full carbocation. But in SN1 reactions, it can, because it doesn't cheat. It ends the relationship with bromine first. And now this carbon is going to take the time and say, I'm now single. I'm now not in a relationship. And it is time for me. I'm putting myself first. And what that means is that this molecule will look at the neighbors. It will look at this carbocation and it will question, can I rearrange? Folks, that's the only big difference between SN2 and SN1 here so far, is that SN2 does not rearrange its carbocations because it doesn't form a carbocation to rearrange with. Wherever the halogen is at, that is where the incoming nucleophile is going to go. That's SN2. SN1, it still gets rid of the halogen. A nucleophile will still come in, just like before. But the difference, the bigger difference here between the two, is that rearrangement can take place. And that's because a full carbocation is formed, and in this case, it's not going to rearrange, because if it goes up, that's primary. If it goes down, that's primary. If it goes to the left, that's primary. There is no better spot for that carbocation. So then the carbon is going to say, okay, I've looked out for myself. I've got my life together. I have everything crossed and dotted like it should be. And maybe now it is time for me to look for a new relationship. I've been out on my own for a little bit. I've not had a relationship for a little bit. I've cleaned my act up. Now I'm ready for a relationship to come in again. And that is when we take our new incoming nucleophile, and that goes on at the location of the carbocation, wherever it decided to happen. All right, so let me give you an actual example here, maybe using that same kind of organic. So CH3, carbon, CH3, CH3, and then Br. And we're going to react this with water. I'm going to tell you a little bit about water and why we've chosen to use it in just a second. So with these two things, we need to show kind of the mechanism about what goes on here. And we have to do this in order. So the very first thing that's going to happen here is that a SN1 reaction is going to happen. An SN1 reaction, how do I know that? I'll tell you in just a minute. So an SN1 reaction is going to happen, and this bromine leaves first. And what that forms is a carbocation. So CH3, carbon, CH3, CH3 down below, and then we have a positive charge that forms. Well, if you look at this water molecule, folks, if you go back and take a look at water when we used it before in the alkene reactions, this is kind of how we drew it, right? So what happens here is that the negative area, which is due to these electrons, are going to be attracted to this carbocation. All right, so just like in the alkene reactions, there's no difference in that particular mechanism. We had CH3, carbon, CH3, CH3 that goes down below, and then here we have an O, and then an H, and then an H that's there. Well, the issue here is that that water molecule now has bitten off two more than it can chew, right? I mean, it was a nucleophile. This is on the nucleophilitic chart. It's not as pretty as some of the others, but it's on there. Why did we use it? Again, that news is to come. But this water molecule is going to go on, and it's going to say, hey, carbon, you want somebody? I'm here. And that carbon says, oh, yeah, okay, not a problem. But when this water comes on, this carbon realizes that that oxygen now, it's got some issues, folks. Oh, a whole lot of issues. Who wants issues? Who wants the drama? Do you want the drama in your relationship? No. And that oxygen and that carbon doesn't want the drama either. So the oxygen's going to have to make a decision. What do? You're the one who said you were ready for a relationship, and now you're in a relationship and you're not ready for it? Now you're in this relationship and you got too much baggage? You need to get rid of something. So that oxygen's going to say, okay, fine. I need to get rid of this hydrogen. Well, and I got a twin. And I think that my twin, this other water molecule, because there's more than one. I mean, it's in a big solvent vat, right? It could be in a beaker, a boiling flask, or whatever. I've got another water molecule at least. That new water molecule will come in and it says, hey, poop. I'm going to pull the hydrogen off. And those electrons go up to that oxygen and it satisfies that oxygen up. So what we end up with, folks, that water molecule allows me to add on a OH group. That's what all of this basically boils down to. So I get an OH group on this molecule, just like we did in the alkene reactions, right? If I took an alkene, broke the double bond, H goes on one, OH goes on the other. OH was the nucleophile. Well, the OH is kind of the nucleophile here as well. Now, layman's terms, that's what goes on. Detailed terms, not quite. But I'm not asking you to be experts here. It might feel like it sometimes, but I'm not. But this is the flow of a substitution 1 reaction, unimolecular, SN1. Carbocation forms, and then a nucleophile goes on to that carbocation. And you have to look out for rearrangement every single time. So now let's talk about SN1 reactions. All right. SN1 reactions, if a carbocation is formed, let's think about primary carbocations, and then let's think about secondaries, and then let's talk about tertiaries. Which one's more stable? I hope at this point you're going to circle this one. And you're going to say a tertiary carbocation is more stable because there's more buddies. Those buddies can help even out that carbon, help evenly distribute that positive charge that might be on there. It's just extra support for that carbon that needs it in its time of need. The primary carbocation, we actually said, was very unstable back in the day, and that story's not going to change. This is a primary carbocation here, this is a secondary, this is a tertiary. That primary carbocation, folks, it just doesn't want to form. I mean, talk about having relationship issues. This carbon believes that it cannot be single at any point in its life. So do you expect this carbon to have a free-blown positive charge? And the answer is no. The molecule really doesn't have a support group, a support network in order to help support that positive charge that's left behind when the carbocation is formed. So we did this with SN2, we're going to do it with SN1. When it concerns SN1, tertiaries are going to react much faster than secondaries, which are going to act much faster than primary. And that's because the tertiary allows the carbocation to form much better, much quicker. Oh gosh. Now I'm going to have to memorize this. I'm going to get these flipped. I'm going to get these confused. Well, I'm going to give you a little hint. Let's write down a summary chart, okay? We're going to have SN2 and we're going to have SN1. And we're going to start with primary. Primary carbocations in SN2s, they're going to happen, right? And that's because this carbon needs to be a cheater. This carbon's not going to want to be alone. It's a primary carbocation. If a primary carbocation is formed, this thing is very unstable and it's not going to want to happen. So it needs to be in a relationship at all times. That is why those primary carbocations prefer to be cheaters. Now you see where this lecture is going. It might have seemed a little hodgepodgey in the beginning, but now I need to put the pieces together and I need to make it sense. So SN2s are going to prefer primary carbocations and vice versa. With SN1, well, this carbon needs to be single. It only needs to see one thing at one time. It doesn't need to be in a relationship at all times. So with SN1 reactions, we don't really have SN1s when it concerns primary carbocations. And this is one of the ways that we can determine which one of these routes go forward. SN2 or SN1. Will carbon cheat or will carbon become single and rearrange? Primaries, carbons never become single. They're too unstable to do it. They need a relationship at all times. Hence, they will cheat every single time that they can do that. All right. Now let's talk about tertiary. I'm going to skip secondary for a minute. Tertiary, carbocation that kind of looks like this over here to the right. SN2, carbon sees two things at one time. Remember the neighbor story? There's too many neighbors here. This carbon cannot cheat because it's surrounded by friends. It's surrounded by neighbors. There's no easy way that that carbon can go in and do that. So when it concerns tertiary, SN2s, folks, it can't happen. There's too much going on. There's no way that this cheater piece can come in and sneak through the back door because there's neighbors on all sides. So SN2 does not happen with tertiary carbocations. However, SN1s, those carbons see one thing at one time. Therefore, they need to end a relationship. And when they end it, they need to kick off the halogen. When they kick off the halogen, they need to be stable. And tertiary carbocations are the most stable out of the three that we've summarized up here on the screen. So tertiaries prefer SN1 over SN2. Now you're starting to see the difference, hopefully. Okay, well, what about secondaries? Let's talk about SN2s with secondaries. When it concerns SN2, carbon needs to see two things at one time. He needs to be a cheater. Well, carbon's got some neighbors next door, but it's not fully surrounded. So a nucleophile could still come in and go through the back door. We said that a secondary carbocation can happen with SN2 reactions. This is perfectly okay. It's not a problem. SN2 reactions can happen with them. Well, what about SN1? Well, that means that this carbon had a halogen on it. If that carbon ends the relationship with the halogen, is it okay? Does it have a support system in place where it can be on its own for a minute? And the answer is yeah. Unlike the primary, the secondary has a support system on either side of it. So this will also work. And now you're seeing the problem with secondary carbocations. These secondary halogens, if the halogen is attached to a carbon that is a secondary carbon, folks, we have no clear-cut decision right now on which one is going to be preferred, do we? Both of these could happen. We could get SN2. We could also get SN1. But we can control it. We can really direct it in one version over the other, and I'm getting ready to tell you how to do that. But right now, we're only focused on carbocation stability. What does the carbocation type mean for substitution reactions? And there you go. Primaries are okay with SN2. Secondaries are okay with SN2. Tertiaries can't happen. Too many neighbors, too many buddies to cheat. As far as SN1 goes, primary can't happen. There's no support system. There's no friends there. Nothing to confirm that carbon made the right decision. That carbon needs to be single. And a primary carbocation, not very stable to do that. But secondary's okay. It's got some friends. And tertiary has even more friends. So it's more than okay. Out of the two, this one is the fastest. And then slower. And out of the SN1, this one is the fastest. And then slower and slower, to the point that we just say it doesn't even happen. There's our comparison chart. Substitution should not be complicated, folks. It really should not be. But it seems like substitution happens at the end of the semester. It seems that substitution's happening with what I call organic withdrawal almost. You're just swamped and swamped and swamped and swamped with classes, typically in a normal semester, that at the end of the semester, when new material is added in and you're trying to scramble and get all of the information from all the other classes that you're taking to at the same time, substitution seems a little bit harder during those periods. It's just the way that it falls in order, though. We have to take care of some foundation issues before we can start building our porch. The same thing's happening here. Right? We had to take care of foundation issues. We had to know what alkenes were. We had to know what double bonds were. We had to know what reactions were. We had to know double bonds and triple bonds break. We had to know about halogens before we started getting into substitution lecture theory. Because it all is really based on everything that we've learned before. So SN2's the cheater. SN1 wants to be single. The cheater, primary is the best suited. It can get in, it can cheat, there's no friends. That carbon needs to be in a relationship. It's too unstable to be by itself. So primaries are best suited for SN2 reactions. And then SN1s, you be single for a while. You clean up your act. You organize your life. But you need a support system if you're going to be single. Otherwise, you're going to be a hermit. You don't want to be a hermit. That carbon doesn't want to be a hermit. So that SN1 reaction needs a carbon that is okay being by himself. It's got some friends to occupy the time. So tertiary is going to be the fastest. Followed by secondary. Followed by primary. Okay. So in the next video, we're going to continue with this discussion. We're going to go through and we're going to talk about maybe some other options of SN1 and SN2 and how to make sure that one version goes over the other one. And we're doing that because we see a problem right in here. Can we direct it in one direction or the other? Primaries, it's okay. Right? We know for sure kind of what's going to happen with primaries. It's SN2 all the way, folks. SN2 all the way. That carbon's going to be a cheater no matter what. Once a cheater, always a cheater. And then tertiary, we kind of know where that's going to go. Tertiary is always going to go SN1 no matter what. It's always going to be SN1 reaction. Tertiary is always going to end the relationship first before it gets into another one. And if it does that the first time, it's going to do it every single time. Secondaries, though, are wishy-washy. Secondaries, you just never can trust them. I mean, sometimes they'll cheat, and sometimes they're loyal, and sometimes, they'll do the right thing. But then before you know it, they'll turn around and they cheat on you again. Nobody wants a secondary carbocation. How are you going to trust those things, right? Well, there's a couple of ways that we can do it. There's a couple of ways that we can introduce something into the relationship to persuade it to do one thing or the other. And we'll talk about that in the next video that's coming up.